So it's a cyclic amino acid, actually, not amino. And even though the side chain is hydrocarbon, and we list it here as a nonpolar one, in reality, this guy's often found in the surfaces where you'd expect a polar amino acid. And it has to do with the cyclic structure. We'll see in a globular protein that we have strands of protein that will come through and they'll do different things, and they'll come out to the surface where the water is, and they'll turn and go back in. And the groups here on the surface we tend to think is where the polar ones are, and the nonpolar in here. But with proline, it kind of violates that distribution rule a little bit. Proline is often right here at the surface because the geometry of this is changed by the cyclic structure, and it puts a bend in the chain. So it's perfect for making the U-turn in these strands. Okay, so we got 8 of those. We got 7 of these polar guys. They have some kind of polar or weakly polar elements in the R group, and so they're more hydrophilic. You can see here, like alcohol groups are common in these, or SHs, or carbonyls, or amino groups. These are water-loving groups. These will form hydrogen bonds to water. That's what makes these polar. They'll be typically more on the outside. But none of these have formal charges. They're just polar. So polar but uncharged. Another one maybe worth special attention is glycine. There's a little dipole character to that. That's why it's in this group. But it's the smallest of all possible R groups. It's just a simple little hydrogen. You might think that Mother Nature, being an economical engineer, would choose to use glycine a lot because it's the cheapest one to make. It has those special characteristics one way or the other. Actually, though, there's some problems. If you have too much glycine in the protein chain, it gets to be too sloppy. But it sometimes, as we'll see later today, is especially called on for virtue of the fact that this group is so small. That makes it useful in some circumstances. But glycine does increase the flexibility because there's no steric hindrance effects because the side chain is practically non-existent, so you can bend sharply there. Another one of this group of polar but uncharged amino acids worth special notice is cysteine. Here's cysteine. Its side chain is a CH2SH. And as this slide shows, if it's hanging around near another cysteine, it's possible for these two side chains to chemically link to form a covalent bond. It's an oxidation reaction, but you can get this disulfide, as it's called. This structure is called cysteine. So the starting one, the natural amino acid is cysteine, can be converted into cysteine, two cysteines and one cysteine, if you oxidize them. Molecular oxygen can do that. So this is a reactive side chain. So these others we haven't talked about reactivity, but with cysteine, its ability to form disulfides makes it useful sometimes as a way of stabilizing tertiary structure. So if you put a disulfide in here, it's like stapling two chains together. The covalent bond is much stronger than the other kinds of bonds we'll talk about. So if you throw in a bunch of disulfides in a protein, typically that makes it more stable. You ever notice the laundry detergent ads sometimes talk about Tide with enzymes, and